Oh, wow. Okay, so I guess I'm ready to start. Sorry again for this projector thing. I was trying to check whether the regular projector works today. It wasn't. Can you actually hear me? How about now? People on Zoom. Ask them. Okay, so sorry. So I see that we lost a bunch of people in the class. So like our attendance actually kind of goes sharply down, which is reasonably okay. But I still would appreciate. And we don't have that many people on Zoom either. It's only like 31 person on Zoom. Like it's a constant number since the beginning. I'm sure I will see all of you for the midterm, which is in a week right after the fall break. Right, so our plan for the next couple of weeks. So today we're gonna start building the CPU, right? So for the last couple of for months, right? So months in a week we were talking about how the interface should look like. We learned the MIPS assembly. Last time we talked about floating point numbers. It's interesting, but probably not as exciting if you don't really do like computations in floating point numbers, and not many people do these days. Unless you're doing like AI optimizations, and you actually wanna, if you do AI now, these days you wanna come from a 32-bit float to a 16-bit float. Apparently it's faster and still precise enough, which is unusual, right? One would imagine that you would only argue for a greater precision, but apparently not. But then so today we start building a simple arithmetic and logical unit, LEU, which will be a heart of our microprocessor. And then we're going to finish building the microprocessor on Wednesday, then a week of fall break, and I hope that you guys will use it wisely and spend time essentially recapping everything what we covered in class. Then will be a recap session right after the fall break and the midterm, right? So are we good with the timeline? Okay. Then let's get going. So the homework, we moved it to Friday, just because people said that you have a lot of midterms this week, and that's fine. But I will assign another one, hopefully before Friday, so you can start working on it earlier. Okay, so today what we're doing is following. We start with gates, right? So, oh, there's a question. Okay, go ahead.
Yeah, the next one will be like Friday or the end of the week.
Good question. Yeah, so I prefer you to take a break on a fall break. So let's move it like in the middle or the end of the next week after the fall break. Otherwise, it's absurd. Break is a break, right? So, but I argue. I mean, I say that, but I still argue that you'll have to revise everything what we covered in class, so you're in a good shape for a midterm. Another question. Yeah, there will be a midterm review, and I'll talk a little bit about everything what we did in class, and then I will talk a little about like potential questions in the midterm as well. Say again? Like a practice test? A practice test. I don't have a practice test. Will you survive? Like essentially, yeah, that's a good thing. It's just because I teach this class for the first time, and maybe I will try to dig what I was teaching in the past. So I was teaching a graded version of this class, which was slightly different. So essentially, the second part of this class will be similar to what I was teaching before, but the first part was brand new to me, and I don't have a test. Usually, I just release the tests, and you can look at the tests from midterms and exams from previous years, but I don't have one. Yeah, I'll think maybe I'll make up a test for you, like a practice test, so you can at least know the ballpark of complexity and what's expected. And also don't forget that it's open book, open everything, so you can. We will prohibit searching online and communicating in any form, right? So, but if you have like and searching, like literate searching, where you type and say, okay, Stack Overflow, like mix something, try to copy the answer. But if you have a book in a digital form or your notes in digital form, it's fine to use them during the test. And search of the book is fine, right? So you don't have to remember anything.
Will this actually be at normal time for classes?
Yeah, so midterm is during our normal class hour, same amount of time. In this room, I mean, we'll have to fit everyone who wants to take it. Good.
Also, it's helpful to remember the kind of keep track of where we are in the rest of the class.
In terms of a grade,
Yeah.
but so you think the homework is not a good indicator for you?
No, I'm saying that where this class is curved. So it's trying to see where I fall on that.
Okay, so I'll try to release the approximate curve. The reason, the way I curve is, I mean, typically homeworks don't get curved because people get max points on the homework. People, depending on how badly I misjudge the audience, the top point on the midterm and final will not be achieved, and then I like set the highest score as the top, and then and then that's the curve essentially. But then there's always the curving of when I assign letters, right? So I have a generous curve. Typically, I can dig it out, but typically the idea is that the person who did maybe more than 70% of the class should pass, and then we kind of split the rest in equal increments between like whatever C or like NA, so along those lines. So usually I try not to. Maybe I told you that, but I don't. I'm not a big proponent of grades, so I don't like giving grades. I would rather, and in general terms, like what I observe in the past, the people who want to learn, they learn not because of grades, but for whatever other reason, just encouraged to do that, and they achieve great things. And everyone else, I think grade doesn't matter either. But I know that when you apply for jobs, I've heard from my students that certain companies do a cutoff on a grade. I don't know if it's true, like in your experience. That's awkward, but I hope you're above that cutoff. And I mean, again, I apologize for like repeating this many times and wasting time on that. The people who work on my team, students, undergrads, I don't know how they got to the point when they got on a team, right? I test them, right? So, and they're pretty good, impressively good. I mean, maybe not that far away from you, but they are there. They get amazing offers, job offers, both in terms of academic offers to continue their career as PhD students, top schools, and like the numbers which they get as a undergrads in terms of salary are impressive today. So again, if it doesn't motivate you, or I don't know, then you should talk to someone who can motivate you. But again, the point is that just try to learn for the sake of making the money back, or doing whatever, gaining the freedom which you get out of it. So those people who, I mean, it's a trade-off. Some people choose money and some choose continued education. And it's okay. Since we're on this topic, my favorite question. It's okay. How many people know that PhD is actually free and you will get paid a salary, so you don't have to pay for a PhD? So if I flip the bit so everyone else doesn't know that. So okay, like master's is, you have to pay for master's degree, right? So in the United States, in most of the United States. And for PhD in most of the United States, you don't pay. I mean, if you work and you don't work for the university, then you have to pay in tuition fees and stuff like that. But typically the way the PhD is set up is that you are either working for a research team or work for the university as a TA, right? So that the guys who are your TAs, they are actually master students, so they are lucky. But in many universities, it's PhD students, and like you get a salary of like roughly $25,000+ a year, which is okay. You can live, but at least you don't like. I mean, again, if you start doing the integral under the curve, and your total salary, well, you will never catch up with a PhD unless you're like build your own companies and become a multi-billionaire. But the freedom and the lifestyle which you get out of it is probably worth it. So again, this deviation from the classes, just to make sure that you understand that if you suddenly want to continue education, I mean, try doing a PhD. It's free. You'll get paid. You'll get a mountain bike. You'll be able to afford a ski ticket. If it's in Utah, you will have a good time. Maybe the best time of your life, to be honest. But it depends again. So think about it. I mean, but if you choose money, the market is good these days, and computer science pays well right off undergraduate degree. What I wanted to say, I forgot. Yeah, any questions about the what is it called, the job prospects? Okay. So a lot of people cannot afford, like when I was in California, a lot of people were not able to afford a PhD just because they are in debt paying for the school already. So they have to recap just because they paid a lot. In Utah, I hope the amounts are smaller, hopefully, for in-state students, right? Okay, back to this. So good, lineup is good, no questions? Okay. Okay, so what I wanted to start on is that like today we have to figure out how we build logical circuits, right, out of those small basic gates. And at the very heart of any gate is this a transistor, which is a 3-terminal device. What it means is that you have voltage always connected here, right? And a ground connected here. And depending on whether you are providing voltage here or you don't, the output of this transistor is either low or high. And in general, like in all these circuits, we will be distinguished at just 2 levels, like low and high, right? And that's kind of like, that's the physics or natural reason for why we're doing everything in a binary form, right? Because, you know, we can treat high as a 1 and low as 0, right? And you'll see how to build simple adders and stuff like that, right? And the way it works is supposedly, you know, if you have a voltage here, tiny resistor here, if you provide the voltage to this terminal, the transistor is in a conducting state, so connected to the ground. So, and if you start sampling voltage at this terminal, you most likely will sample, not most likely, but you will sample the low voltage. And vice versa, if you supplying low voltage to this terminal, then the transistor is not in a conducting state, then obviously you will have a high voltage here, right? And you can see that this is an inverting circuit, right? So essentially, if you're providing a high voltage here, then you get an invert of it, low voltage on this output, right? And vice versa, if you're providing a low voltage here, you'll get a high voltage here. It turns out that from this trivial gate, so this from this trivial transistor, you can build more sophisticated logic blocks, which are called gates, right? And essentially from gates, you can build various circuits, right? And there are specifically 2 flavors of those circuits. So if a circuit is just depends on its inputs, so essentially you have a bunch of inputs, you have something here, some logic of those gates, and this like simplest gates are like built out of those transistors are AND or not, and so on. And we'll cover more of them today. But essentially, if the output of or outputs of these circuits depend only on the inputs, right? Then it's called a combinational circuit. So essentially, the high-level observation here is that there is no memory. And on the opposite, if you have some kind of state, the circuit has a way of keeping a state here. And the input of this, the output of this circuit depends not only on the input, but on some other state which the circuit's seen in the past. Then it's called a sequential circuit, right? And today we mostly spent building simple combinational circuits, and then later we'll introduce the idea of how we can introduce, how we can build this state keeping logic, right? And then we will essentially introduce the cloaking methodology as well, and where we'll build like a tiny MIPS CPU out of it. But today our goal is to essentially understand how we can build simple circuits, combinational circuits out of and or not and so on gates, and essentially build a simple adder. Any questions right now? Good. Yeah, well, nothing super interesting. And so how we reason about the circuits, we have to define specifically what is it we want, what kind of how the inputs and outputs are related, right? And so consider an example in which we're building a circuit in which there are three inputs, A, B, and C, and an output E, just one single output, right? Although it doesn't has to be the case. You can have multiple outputs easily, right? And we want this output to be true, or let's say high, right, or 1, only if exactly 2 of the inputs are true, right? And we say, look, okay, let's build a truth table, right? So roughly speaking, it should look something like this. And you say, so if A and B are zeros, but C is high, then obviously E is low, because our condition for E to be high is that exactly 2 of those inputs are high. And so we can take a look here, for example, B and C are true, right? And then E is true as well. A and B are true, right? E is true. A and C are true, right? And E is true, right? And that's it, because if 3 of them are true, then E is not true, because that's not what we want, right? So when you say, look, okay, I can define my digital circuits with these truth tables, and it's fine, but really they don't scale very well, because if you imagine that you have a bunch of those inputs, like even something like 32, right? In case of our CPU, if we're building like a 32-bit CPU, then it's hard to it's hard to keep track of what's going on, but also it's hard to understand the semantic meaning of this circuit, right? So because even if I give you semantic meaning here, right? And it's easy to capture and it's easy to remember in your head, but by looking at this truth table, it's kind of hard to reverse engineer this meaning, right? So you have to really stare really hard to make this conclusion, right? And so what people's doing instead of using truth table, people using Boolean algebra. So Boolean algebra is just a notation which essentially allows you as a human to say, okay, when the output becomes true depending on the inputs, right? And those equations in Boolean algebra, they follow this 3 primary operators. So one is a operation is OR, and a symbol is a plus. So essentially, which means that the result X of A plus B or A or B is true if at least one of the inputs is true, right? And you can obviously construct a truth table and say that, okay, this is A, B, and X. If A is high, 0 low, X is high. A is high, B is high, this one is high. If this one is 0, this one is 1, this one is also 1, because as long as one of them is 1, the output is 1. And only if both of them are low, then this one is low as well, right? But it's easier to write it like this in a human readable form, right? A plus B instead of a truth table. And you'll see soon how like scaling works better with this Boolean algebra equations, right? So AND operation is identified with a dot, and essentially you write A dot B, and the result of this operation is true if both A and B are true, right? And again, I can start the truth table, and you will, like, it will respond to what you naturally assume it should do, right? And not is this bar symbol here. So A naught or A bar equals X. So it's inverted value of A, right? So essentially, if A is low, then inverted A is high. If A is high, then inverted A is low, right? Okay, reasonably simple. There are specific, like any algebra has rules of addition, associativity, commutativity, and stuff like that. So some of those rules are kind of natural and some are less natural. So let's like just briefly, why are those useful? Essentially, you say, look, why do we even care about it? The idea is that if you get a complicated Boolean equation, sometimes you use those Boolean algebra rules to simplify it. So it's very similar how you were in elementary and high school, you were using what is it called? Linear algebra rules to essentially simplify equations and come up with simple answers, right? It's the same here. So for as long as you can simplify a complex Boolean algebra term, then you get with a simpler one, and your logic, your circuit logic is equivalent, right? It will turn high on the same inputs as the complex one, but it's easier to build and will have a smaller delay, for example, in terms of gates, right? So this one as identity law is reasonably natural. You say, like, no matter what A is, A or 0 stays A, right? Because zero doesn't change the value here. And similar, A and 1 stays A. 0 and 1 laws. So essentially, if you add or with 1, you will always get 1, and that's again kind of like you can check this with a truth table if you don't trust your intuition, but in most cases you can probably trust here. And vice versa, if it's A and with 0, you will always end up with 0, just because, you know, that's the definition of and, right? Inverse is A and not A equals to 0, because you can observe that one of these two will always be 0, right? And so n turns into 1 only if both of the arguments are 1, right? And A or not A is always 1 for the same reason, because one of this is bound to be 1. And so by this law, essentially A plus 1, you will always get 1, right? The commute, and you say, okay, commutativity, it's interesting. So this, do we ever encounter a non-commutative operation in computer science yet? Do we have it? Or we don't. I came up with look, okay, commutativity is there for both or and, but let me ask you the following question: associativity. So it's an associative operation. So A and then B plus C is the same as A plus B plus C, right? And if I ask you a question, so did you encounter in this class, can you give me an example of an operation which is not associative? We've seen it before. So you're saying that division is not associative, meaning that associativity for division is kind of like 16. No, division doesn't count, so it's not associative. But like, imagine you have something like a plus. Can you imagine a definition of an operation which is similar to plus, which is not associative? Yeah. Do you have an example? No, that one probably counts actually. So yeah, left shift is a great example, I believe. So what do you have in mind? So you're saying something like, well, like 1 left shift 1 left shift 2. Is it associative or not? Maybe it is associative. I don't know the answer, most likely. Okay, let's think about it. But my example of not associative operation, which I forgot to mention actually last time, is floating point operations. Because of the rounding, and this is a little bit counterintuitive because this is a real problem in practice. Because of the rounding, so if you have 3 floating point numbers, the associativity of the addition operation, for example, matters. Because if you add 2 numbers, B and C, and then add A, and vice versa, if you add A and B and then add C, they might not, you might get different results because of the rounding rules, right? And it in practice, you might observe this if you're running like a multi-threaded workload, and you, for example, saying that I will be splitting the work in some or in some way, and like those threads will be picking up the work, and in the end, it's just a bunch of additions, right? So you would assume that maybe you want to add all elements in the array, for example, right? But you say like I will be adding subsets of the array just to do it in parallel on multiple CPUs. So depending on the interleaving of threads, you will get different results or may get different results because just the floating numbers, the floating the floating addition is not associative, right? So like, and this is, it's there in the book in one of the chapters. So essentially, if you just say I have a bunch of floating numbers, F1, F2, F3, F4, if you have to find a sum, you say, look, I will like be running like, for example, even 2 threads, and like the thread picks up maybe like these 2 numbers, and then these 2 numbers, and so on, and maybe like you put back intermediate addition somewhere, and that's a real problem because for those floating point operations, you say, look, I expect it to arrive to the same number, but it's slightly different all the time, and you can just to give you an example, which of like roughly speaking, even an integer addition can follow this rule, because if these are 2 large numbers and these are 2 small numbers, so large, small, small, or like even negative, right? So if you're adding 2 large positive numbers, you immediately get an overflow. But maybe if you would add it like large and this one and this one and this one, the result would not be an overflow, right? So just another example why overflow, and it's similar in both floating points and in integers. So you can arrive to the case where you can either get an overflow or get an answer, a valid answer. Person.
What about exclusive work?
Exclusive OR. No, exclusive OR doesn't result in any kind of overflow, right? So it's just bit to bit, right? So that will not break associativity, I believe. So it will stay associative, right? So an exclusive OR is actually can be expressed as we'll see it in a second, as a combination of those primitive operations plus negation, right? So if one of them is associative, then that's the rule of the algebra, then the other one will be as well. If you can prove it, I guess. Okay, so distributive laws, like we have this one, typically, like this corresponds to the linear algebra, right? And this one doesn't, but it still works the same way. And the way to prove it is, for example, to construct the truth table for the left and the right part, and just prove that actually this distribution works like that in this specific algebra. So this is the law which is like unusual with respect to linear algebra, right? Because typically there is no distribution with respect to addition, right? Oh wait, there is one other law which is called De Morgan's law, which means that A or B and then negation is the same as A negation and B negation, and vice versa. A dot B naught is the same as A naught plus B naught. And again, so if I ask you in a homework to confirm that these are true, the way to do that is to essentially construct a truth table and to prove the equivalence, right?
You have the bar over the operation, so like A or B, and that can get whatever that result is.
I maybe I misunderstood, but what you're saying is that imagine you have some kind of a term and then negate it, right?
Yeah. What's inside, so like in this case, A, or that you would invert that.
No, that's essentially the law, which says that you can either treat it as a like some term, like a black box, let's say X, and then you can compute X and then negate it, right? Or if you don't want to do that, so an equivalent operation would be essentially just follow the De Morgan law and essentially say it's A not and then and not B, right? And it will produce the same function.
My confusion is just like the order operating. What did you invert A and then it would be?
Oh no, like no, this is how you read it. So it's treated as brackets here. Like you first compute this one, and then you negate it. But it's the same as treat them in this form, equivalent logic. Okay, so now we understand enough about this Boolean algebra. Let's become a little bit more ambitious, and we'll try to build a simple arithmetic logical unit. And it's you'll be surprised that it's actually easier than you think. So for drawing digital circuits, people came up with this visual representation. So essentially, this is a AND gate, this is a NOR gate, and this is a NOT gate, right? And so sometimes instead of like drawing the entire NOT, they just draw this bubble. So this is equivalent. So this thing, which is take the output of this gate and essentially negate it, is the same if you just put this bubble, just to simplify to make the drawing simpler and shorter, right? So if you look at this picture, let me just erase everything on the slide. What logic function is this? Who can write it down? What happens here?
So I would do this, get this non-parentheses.
Not about, yeah, because this is this one. Okay. Not A or B, correct. And it's the same according to the De Morgan, right? So if you want to simplify this, you can write it as A and not B, right? Agree? But this is right. So you can either assemble it from the backwards, like your classmate did, or you can assemble it forward, saying that, okay, what happens to the input A? Input A is negated, so it's not A. What happens to these two inputs, A and B? Okay, here and here, they're provided as an input to the OR gate, so it's not A plus B, and then the whole result is again negated, right? So you see the correspondence, so you will be able to read what's the logical, like just a Boolean notation and this pictorial notation as well, right? And so again, remember, I started this by saying that it's easier to use this Boolean algebra to write down the functions and see the meaning of them. So essentially, if we're coming back to this example, which we had before, which is the output E is true exactly if two of the three inputs are true, we can come up with like different notations, right? And so it's you can either say that the whole circuit will become true if both of these are true. So A and B, for example, is true, or B and C are true, or A and C are true. At the same time, this is this and this is not true. So A and B and C cannot be one, right? So we want to essentially eliminate this case where three terms, both of them are high, right? Or if you think about it differently, you can also say that this output will become true if A, B, and C, right? Not C, I mean, sorry. Or A, C, and not B, and C, B, and not A, right? So this is exactly like essentially writing down the same truth table, but in terms of Boolean algebra. And this notation is specifically convenient because you can quickly see on what inputs this function becomes true. It becomes true exactly when A is 1, B is 1, and C is not 1, right? So it has to be 0, or it becomes true when A is 1, C is 1, and B is not 1, right? Or C is 1, B is 1, and A is not 1 or is 0, right? So one of these three cases is will give you a high signal, right? And you essentially can use the laws of Boolean algebra to essentially prove that this and this are equivalent, obviously, right? Or you can build a truth table again if you don't trust yourself or don't know how to use the rules of Boolean algebra, right?
So back to the previous slide, would a identical, I guess, logic gate, the one with the 3 logic, the and or not, would an identical gate just be an A, like a solid A line with an AND gate, and then a circle to that AND gate, and that's it?
Which one? So this one or the previous one?
Basically the 2 on the bottom mean the same thing, but I'm saying if you wanted to just use an AND gate, would it be the same to just say A with a straight line going into an AND gate, and then a B with a circle, so a not B going into the AND gate? Is that just the same thing to say A and not B?
Right, exactly. So this is how you, and this is exactly, so if you have a proof that this one is equivalent to this one, right? Then obviously this implementation, which is this one, right, is equivalent to if you take A, put the AND gate, right, and you invert input of B here, right? So that's exactly the same, right? And so you as a designer can implement it in 2 different ways. Yep. Okay, so essentially, like again, so this is an easy rule for how to convert from the truth table to this form, which I was using here on this slide, which is called a sum of products, because each of the element here is a product and it's a sum of them, right? So essentially what you're doing here is, if you have a truth table, you say on which inputs the output turns into 1. So, and then you essentially, that will be one of your products, right? And then you say like, but what is this product itself? It has to be not A, B, and C. So this is this one, not A, B, and C, right? And then since you have 3 cases in which this output turns 1, becomes true in Boolean algebra, so essentially you write down those products, right? And this is the notation which is convenient because for multiple reasons, it's easy to understand and it's also easy to build. And there is also specifically, there's a logical circuit to which you can essentially say, I will only have 2 blocks of these. Like the first level of blocks will be just doing the AND operation, and then the second level of blocks will be just doing the OR operation, right? And so that's a convenient notation, and you understand how to quickly move from a truth table to this sum of product notation and back if you want, right? And essentially, this is kind of key for constructing like the adder, which we'll do in a second. Okay, let's take an example. So there's a couple of other circuits which are popular. So or a couple of other gates. So not AND is a negation of AND. So essentially, this is the notation A NAND B, and this is how you write it. So A and B, and then negate it, right? And NOR, which is A NOR B, or A and B negated, right? A plus B negated, right? And apparently those are universal gates. So essentially, if you use just NAND or just NOR, you can actually build any Boolean circuit right out of it. Although just it has power, so it's equivalent. So essentially, you can prove it that you can construct any logical function. But we're not going to do it just because it's easier for us to manipulate with AND OR gates, right? Because of this notation which we introduce here. So sum of products, right? And just a couple of examples which we will like frequently see while building this simple MIP CPU. So one of this is a decoder. So essentially the idea here is that you have some number of outputs, like in this case, it's 8 outputs, and you provide a number which essentially encodes which of these outputs will be activated. So in this decoder, exactly one output is high for each of these numbers. So kind of like you can think of it that you providing a number from 0 to 7 here as an input, and you get one of those lines, sorry, activated, right? And this specific decoder logic is typically used to implement memory, because you can think of it as, imagine there is some storage thing, right, which essentially consists of multiple lines which remember some numbers, right? And then if you put this decoder in front of it, right, and you say, look, this is an address, and so for example you say like if it's 32 bits, right, so it's allows you to encode and activate essentially any of those lines, and this line becomes read and, for example, placed in the register. So decoder is useful. And to a certain degree, the invert to the decoder is a multiplexer. So the multiplexer circuit is the following. So if the multiplexer has multiple inputs, in this case it's just 2, right, and you have a control signal provided to it, right? So and the relationship will be, you need, like, depending on the number of inputs, you will need a log of 2 of this number control signals here. So for example, to select between 4 inputs, you will have 2 control lines here, right? But in this example, you essentially say, it just, I'm selecting between these 2. And what it does is that, for example, if the control signal is 1, it just short circuits or short wires this input B to the output C here. And if it's 0, it passes this one through, right? So it's very useful, and we'll see it when we will be building this LU device, that you can, depending on which signal, the LU will be computing multiple outputs, but then we will be choosing just one of them as a final output, right? And just to convince you that it's easy to build this multiplexer, imagine this is the circuit. So like if we provide S as 1, right? So here's a little bit of notation. This black dot means that those 2 wires are connected. Essentially, they are wired together. And these 2 without a dot, they are not, right? So just like 2, one on top of another. So if we put S as 1, let me just erase everything on this slide. If we put S as 1, then we will have 1 here. If we place B here, so B on the output here, we have B and 1, right? Which is still B, right? Always. On the other hand, since this one is an inverted of S, so this is 0, so this is A and 0 is always 0, right? And so, and 0 plus B, according to that law, is always B, right? So if you provide 1 here, you get output B here. And vice versa, if you provide S as 0, right? Let me just quickly change color. You will have S is 0, so you will have 0 here, B here, so it will be B and 0, right? So it's always 0 here, and vice versa, inverted S will become 1 here, so it will become A and 1, right? So A and 1, according to this Boolean algebra, is A itself, so it will be A or 0, which is A itself, so you will have A here, right? So this is just a way to construct this multiplexer. Any questions? So far, so good. Yeah, let's keep moving. And now the error algorithm. So we essentially say, let's try to think about how we can construct a simple error. So just imagine, just for the sake of example, just quickly review how the addition works. So on a 4-bit numbers, so we have 2 4-bit numbers. One is 1001, one is 1010. So we adding this 1 plus 1, we'll get a sum of 1 plus the carry of 1. So this carry goes here, like, or in this picture it goes here. Then you add 0 plus 0 is 0 plus carry Oh, okay, yeah, so carry comes here. So 0 plus 0 is 0 plus carry 1 is 1 is a sum. Carry itself is 0, so we have carry nothing here. 0 plus 1 is 1. Again, carry is 0. So carry here 0. 0, 1 plus 0 plus carry 0. Essentially, it's 1. And a carry again is 0, right? And if I ask you, if we quickly review it and we say, look, this adder algorithm, it has 2 inputs, or actually it has 3 inputs, right? Because it's A and B themselves plus the carry in, which comes from a previous bit, right? For example, if you look at this one, you have 3 inputs. So the carry itself and A and B, right? And it provides 2 outputs, a sum and a count. So what will be the truth table for this example? So let's consider the first line. So A plus B sum is what? 0 carry, 0, just because carry here was 0. So the same example, but A plus B plus carry 1. 1 carry, correct. This one, sum is again 1 carry 0, right? So if we got the point, so essentially this will be the truth table for the sum and from the count, right? And for the carry, sorry, agree? And so remember this notation where we essentially take, for example, the sum function and turn it into a sum of products, right? So we take a look at the inputs on which it turns 1. So we know that there will be 4 products, right? You guys, do you have a question? I can maybe answer a little fast.
Sorry.
No worries, but is there anything what needs to be? Okay, so the idea here is that again, so we're trying to construct this logical function for the sum, right? So we're saying, okay, on which inputs it turns 1? It turns 1 on like not A, not B, and a carry in. So specifically that, not A, not B, and a carry in. Then it turns 1 onto not A, B, and not carry in. So it's, which one is that? A, not A, B, and not carry in. So this one. Then this one, which is A, not B, not carry in. A, not B, not carry in. And the final one is when all of them are ones. So it's A, B, and carry in, right? So this is your, essentially, this is your Boolean function for the sum. And if you do the same trick for the count, carry out, then you will have these 4 products. And if you start simplifying, for example, this one, according to this De Morgan law, or no, it's associativity, right? So it's, for example, A, B, carry in plus A, B, not carry in, right? It can be simplified as A dot B plus carry in plus not carry in, which is A dot B. This one turns into 1, right? Or it turns into A dot B, right? So that's a simplified form. And then you can simplify this too as well. You can do it at home, right? So, but essentially, so first of all, like it's useful to have this sum of product notation, right? Quickly convert from truth table to the Boolean algebra, then use a little bit of Boolean algebra laws to simplify the term, get a simpler term, and now you can actually use a drawing notation to draw those functions, right? So, for example, if I take this is my logic block for carry out, right? So this is the carry out function, and this is the simplest form which we can arrive to. So essentially you say, okay, so there is will be an OR of 3 products, right? And each of these products, so one is, for example, A and B, right? So essentially it's this one, A goes here, B goes here, right? This one is carry in, so I can write here. So this one is A. What are we doing here? it's A dot B, right? This one is A dot carry in, and this one is B dot carry in, right? And this is a giant OR, which takes three of them, and essentially this provides you the carry out function. Agree? So essentially, if you physically have those logic gates and you have some kind of a board on which you can connect them, that will be your, if you connect them in this way, you will get this carry out function, right? So far, so good. So was it, did you get how we constructed it? So truth table, that's exactly, I mean, there is a couple of questions. So like, first of all, did we enumerate all possibilities? I mean, we did, obviously, right? So it's essentially, if you like, it's all possible inputs for A, B, and carry in, right? And then we just filter out the ones which we don't care about, where the function turns 0, but pick the ones on which it turns 1, convert it into this the sum of products notation, and just essentially simplified it and build a pictorial representation, right? Good. So right now, this what happens here is this element allows you to add 2 bits, right? So you have a bit of A and bit of B. You have a carry in, possibly from a previous bit addition, and you will provide a carry out function. And you can similarly construct a sum function, right? So now if we want to add a couple of other operations, because remember, our goal for this LU to be able to do addition, subtraction, we want to do and or operations, right? And we will also do a negation as well on the bits, right? So because we want to operate on 32 bits. Right now, let's first construct this basic block, which allows us to operate on 1 bit. So we can easily add this and or operation by essentially say that if we already have this black box, which we constructed on the previous slide, which essentially here produces a sum and here produces a carry out. And the reason we kind of phase the carry out downward is because we will be able to connect it on the next slide to the next subsequent bit. Remember, because the carry out always goes to the next bit, right? So if we add 2 additional gates here, we add an AND gate and an OR gate, and NOR, we say, what if we put a multiplexer here? Because we will still take A as inputs to all of these gates, and it will go to our black box as well. But now we will do a multiplexer, right? And here we can choose an operation. So essentially we say we will use 2 bits, 0, 0, 0, 1, 1, 0, and 1, 1. And we can use a subset of this, like of this 4, for example, use only 3 of them to essentially pick either the result of the AND operation, result of the OR operation, or result of the addition operation, and provide it as a result of this, the whole circuit, right? So it's kind of the heart of this LU, which will allow you to do AND, OR, and addition right now, right? Does it make sense? So now let's see how we can connect them together. So remember I said that if we have this basic block from previous slide, and each of them operates on an individual bit. So for example, this operates on bit 0. Like you have inputs A and B, right? And A has A0, B0 here, A1, B1, A2, B2, and so on until A31 and B31, right? So those are individual bits. This is the lowest, and this is the highest bit of the number, right? Of the binary number. Go ahead.
So for that main 2 bits,
Yeah. So in this specific, okay, so why does it make sense? So because if we look at this circuit, people reason in terms of those gate delays, and gate delays are in the order of picoseconds, or even like fractions of a picosecond. But essentially this circuit has a delay of 2 gate delays, because it's 1 layer of gates here and then the second layer here, right? So it's okay to essentially, and this circuit will have the same, because remember this one had also 2 layers for this multiplexer, and I think it has more layers for the one which is chooses between 3 inputs, right? So roughly speaking, these operations can be performed in parallel. And the disadvantage here is that those elements still will consume some power, right? So they will consume some energy and will dissipate some heat. So, but I guess in this specific example, it's just fine. But you can, if you're using a lot of them and they don't do anything, there is like a static and dynamic power. And essentially, if at some point it can become a problem, and it's beyond our class, I guess, at what point it becomes a problem. But in terms of latency, they don't change anything, right? And so we say, like, why not to perform them in parallel? And this is how it's done here. So any other questions about this simple 1-bit logical unit? Okay, so how we connect them together? So essentially, they will operate on individual bits. So bit 0, bit 1, bit 2, and up to bit 31, right? All the same block, which we had on the previous page. The operation itself is always wired here to choose whether we're doing addition, subtraction, or and, right? Oh, sorry, addition, and, or. And we'll see how to do the subtraction in a second. Carry in, we'll talk about what is this initial carry in a second. But essentially, if you're adding 2 bits and you have some carry out result, then it's piped as an input to the next level of bits, right? And so on, right? And essentially, each of these produces 1 bit of result, right? Make sense? Do you believe that it will add your 232 numbers? Or, okay, cool. So now let's think of how we can do subtraction on it. So what do we remember how we subtract 2 numbers, or can subtract 2 numbers? We can obviously build again a truth table and everything like that, but we can easily make an observation that it's very easy to reuse the same addition, but just do what? Right, exactly. So in practice, so A minus B is the same as A plus minus B. And what is this minus B? Remember, what is that? It's not B, but what else? Plus 1. Right. So this is exactly what we're doing here. So we say, okay, we can easily turn and invert all bits of B. For that, we will introduce this inverter here, right? Which will take the bit of B and invert it. And we will introduce a multiplexer, which will either choose the original B value or we'll choose the inverted B value. And we will use it as a control signal to this inverter, right? And this signal then will go to our black box, right? And so which means that if we have like 32 of those, and if we provide B invert as high, right, as an input, then we will get B inverted as an input to our circuit, which does the addition, right? That's inverting B, but we need also to provide plus 1. And so for that, we will be using this carry in. Remember, on this circuit, there was this additional carry in signal. So normally when we do an addition, it's 0. When we do a subtraction, we switch it to 1, right? And at this point, we say, look, that's like adding 1 because you already have 1 carry in bit introduced into this logic, right? So and it will provide you a subtraction. So here for this operation, you still choose addition, right? But however, you set B invert to 1 and carry in to 1, right? And it will allow you to, it will implement subtraction, right? Any questions? Okay, so let's, since we said, okay, we want to add additional operations like not or and not and, that's reasonably easy as well. So we'll do the same trick with A, right? So add an multiplexer which chooses either the A signal itself or inverted A. So this is A inverted, right? And essentially, if we say we want to do something like, if we do something like not A and not B is by De Morgan law is the same as A plus B not, or this is called not or, right? This is how we essentially by providing these two signals as high, 1, 1, and then choosing this operation as do the OR, we will get an OR circuit, right? And if we do an AND, we do the same. So essentially not A plus not B. De Morgan tells it that it's A, B inverted, right? Which is not AND, right? So this is easy, but just adding the same inversion logic to A and using it in conjunction with inverting B and specific operation. So what else is missing? So we have, right now we have addition, subtraction, we have AND, we have OR, we have NOR, and we have NAND, right? Do we need anything else? Any other logical operations? Bit operations. So what is XOR? It's XOR is if it's 2 zeros, then it's 1. If it's 0, 1, it's 0. 1, 0, it's 1, and 1, 1, it's 0, right? Correct? That XOR? Say again? Say this again. Which one is exclusive for? I forgot already.
So now you're on 0.
This one is 0?
0 and 1 will be 1.
Okay, got it. 0 and 1 will be 1.
They're exclusive or, right? Either or
Okay. Embarrassing. Let's look it up. What? Introduce in Excel. Okay, so it's essentially saying that exclusive XOR is like this. It's 0, 0 is 0, 1, 0 is 1, and 1, 0, 1 is 1, and 1, 1 is 0, right? That's XOR. So how can we build it quickly? No, let's. Do we see how to build it? Does anyone see the answer? I don't right away.
two cases are not A and B, or not B and A. So like the algebraic equations.
So it's negation of or essentially?
No, so like if you have like the equation, it would be A not and B, or B not and A.
For whatever reason, I don't see the answer, but let me take. It's a sum of products. So what sum? Okay, tell me. Oh, which one?
That was just how, that's like the logical way to make OR, but so pretty much the OR table is if both inputs are 0, then it's going to be 0. If only one input is 1, then it'll be 1. And if both inputs are 1, it'll be 0. So those are the, I guess, technically 4 states. So then if you look at the 2 true states, then it would be 1 and 0 is true, and 0 and 1 is true.
Yeah.
So then it would just be not 1. But then you can change it to
so, but this is the truth table for XOR, right? But I don't see how to build it out of those elements for whatever reason. You see how to build it?
yeah, so if you have
So like earlier, we were doing the two statements, looking at the truth, it should only have one output. I don't know why you have four. It should have two inputs and one output. So I think that's the confusing part. I don't know why you have four.
No, I have, these are the states, like, those are my inputs A and B, and this is the output XOR, just the states. It's a truth table.
Oh, sorry, it's a sideways truth table.
Yeah.
Never mind.
No, but I don't know how to build it, right? So let me think about it, and I will come back to you next time. But just keep moving for the sake of it. But I somehow don't immediately have an answer. Well, it should be possible. Okay, so let's like build a couple of other instructions. So we have 10 more minutes, right? So, or 8. So remember this set less than operation, right? So which was essentially SLT takes two registers as 0 as 1, for example, and sets this one as 2, for example, if as 0 is less than S1. Agree? Right? So this can either be a 0 or 1, right? So just two values, right? So it's true or false, right? So how can we build this operation, set less than? So since we know how to compare numbers, right? So essentially we can perform a subtraction and essentially just check the sign. So essentially if you have two numbers like 7 and 5, then if you subtract 7 minus 5, it's 2. And then you don't really care about the result of this subtraction, but you know that if it's a positive number, then 7 was larger than 5, right? And vice versa, if you do like 5 and 7, right? You subtract 5 minus 7, you get -2. And again, you don't care about the 2, but you can get, just look at the bit, which essentially tells you whether the number is positive or negative, right? And so we can change this circuit to essentially, what we can do here, we can use the same subtraction operation, right? So which means that we have to invert B, provide a carry in, choose the addition here as an operation, right? And what we care about is we only care about the very last, the 31st bit, right? And we will take this bit and essentially we'll say like the result which we want to expect is like 0, 0, all the zeros, and the very last bit is either 1 or 0, right? So we will take this less for all bits, it's always just simple 0, right? And then we have to change this operation to essentially, instead of just doing add, just doing some new operation, right? And the very last bit will be wired, so the bit 31 will be essentially from here will be wired as an input to bit 0 of the result, right? And so essentially what it will give us is that we will subtract the numbers, choose this last input, which is always 0, right, for all the bits. But for the bit number 0, it will be the result of the bit 31 of the subtraction, right? And so that will provide us the essentially the set less than, right? Do you agree with this? If we, so this is specifically the circuit here. So we take this, for example, the result of the 31. How do we do this? The way it's constructed is that we take all the results here, right? Since on all of this will be essentially the result will always be 0, right? And we take essentially a giant OR gate, and if this one is also 0, then all of these are this one is actually this, I believe that this one is actually, this one is implementation of a branch equal, Okay, let's quickly take a branch equal, and then I will explain how we can achieve both with this single circuit. So remember, branch equal is essentially what we care about is that we have two registers like S0 and S1, and we branch to a label here, right? So we just need to detect whether these two are equal. So how do we do this? Yeah, so exactly what it says here. So subtract both. So S0 minus S1, and then essentially check if this one, the result is 0, right? And this is what we are doing here with this circuit. So essentially what happens here is that we take result of this, like, and pipe it to a giant OR gate, take bit 1, again, pipe it to not only to the original output, but also to this one, to this OR gate. And so it will be like 32 OR bits, right? And essentially, if all of them are 0, right, then this output of this gate is 0 itself, right, because it's an OR, and we negate it, turning into a 1, saying that, okay, we detected that the result is actually 0. And then this result is piped to the control logic of the CPU, and essentially it will like essentially change the program counter, saying that it's a jump to the label. And we'll see it like next time. We'll see how this program counter will be incremented. But here, so if we were talking about the previous one, which, and I got confused here, but essentially, where is my bit 31? Where does it go here? So this is my less input, right? So essentially, all this, remember, we wanted to do a set less than, right? And it's all of this are zeros, including bit 31. This is my bit, which is an output of bit 31 subtraction, right? And if it's a negative number, so essentially it becomes 1 here, and this one is piped as a less input to this bit 0. And so this one will provide like, since our control logic here will choose the less signal instead of like a real subtraction result, right? So we don't care about the result of the subtraction. In this specific operation, we will choose the less, and this less comes from bit 31 of the last bit addition. So this one will be, if it's a negative number, it will be 1, and if it's a positive number, it will be 0, right? So essentially, if it's less than, if A is less than B, so it will be, for example, 5 minus 7 will be a negative number minus 2. This bit will be 1 because this bit will be 1, and that's essentially how we detect this result. And everything else will be zeros just because we chose 0 from the last signal, right? So that's what I was confused by, because ideally I didn't want to see this part of the circuit in this picture, but it was there already. So okay, so what did we achieve? Just real quick. So right now we have all these wonderful operations, right? So we have addition, subtraction, we have and, or, set less than, we had NOR and NAND, and we have branch equal, right? So it's pretty much puts us close to what we wanted, right? And then from taking this LEU, we will build the entire MIPS machine next time. So thank you. Let me just stop the Zoom recording.